Okay, so before I start, as I told you, we will have an exam between in the week of 16 to 20. Okay, so what is a good time of the day to have the exam? Huh? Yes, okay. So 18th is what day?
Wednesday.
Okay. So what time is good? Because it may take you maybe 2 hours, 2.5 hours. I usually give 3 problems. I have not made the exam yet, but so
2 p.m.
2 to 5 you will be free, right? I mean, then you shouldn't have labs and this and that and all. So Wednesday 2 p.m. is fine. And can you sort of also say speak for the people who are not around? It's okay, right? There's no real conflict at that time. Okay, so tentatively let's fix it for Wednesday, and I will send out an email about it. Okay. So that's one thing. The other thing is that Tuesday is Holi, so I think that will be a holiday. I'm not sure. So we should have a lecture on Monday. Okay, so there'll be a lecture Monday next week and Friday, because as I checked, you people said that 1:30 Monday is okay for any alternative lecture, right? So there will be a lecture on Monday.
So what is the syllabus?
Yeah, so I'll tell you on Monday, but certainly all of this is there. I'll tell you where to stop, but everything up to now, next lecture, and possibly Friday of next week. Okay, so all of that will be there. All right, so recall that I had told you we had looked at types of interaction terms that you can use to build a matrix element that is a Lorentz scalar. Okay, so the scalar term, pseudo scalar, vector, axial vector, tensor. Now I've written down the specific form of these, okay, in terms of the fermion bilinears last time. Alright, is this clear? Now these and combinations of, so either you pick a scalar or a vector, or you pick a combination. They are all acceptable ways of, but it's not just Lorentz invariance. It is also the fact that the answer that you get for your cross section for scattering or annihilation or decay must match the experimental value that you measure for that scattering or for that decay or whatever. Is that clear? So the answer will change depending on these choices that you make. So you may get a scalar, but it may not match the total decay rate, or it may not match the decay angular distribution or the decay energy distribution. So you have to take all those things into account when you build an interaction. Okay, is that clear? So that combination which gives you correct answers not for just one quantity but for multiple quantities is what you have to choose. Now, if I choose something for the weak interaction, it should work for all weak interactions. I can't have different choices for different weak interactions. That should be clear. It's a Lorentz invariant, it's a vertex choice. So for electrodynamics, it's IE gamma mu. And every vertex that I take will have that strength and that Lorentz structure of a single gamma mu sitting there. So similarly, I have to develop for the weak interaction a consistent choice. Okay. Right. So, as I said, they were seeing these new interactions, they knew they are not electromagnetic, they knew they are not strong, and they're trying to build the Lagrangian. So one possibility. For weak interaction, Wi is weak interaction. So I could perhaps make a choice of a vector. So that would be, now let me introduce a new coupling because it's not electromagnetic anymore. So whatever it is will be some coupling characterizing the new interaction. Okay. So there's a coupling, and then I'm using muon decay as my representative or template interaction for weak interaction. So this is a mu and not a u, and there's E plus charge conjugate. Okay, because the total Lagrangian term must be real. Alright. Now, you see, this term is a product actually of 4 spinors here. Alright. That's what. Why is the interaction term like this? First of all, remember that the interaction term has to have dimension 4. This is already dimension 6. Okay. So that means this must have dimensions of 1 over mass square. This new coupling. That's not the same dimension as what you had in your scalar phi-4 theory or in your electrodynamics. E was dimensionless. So that's one difference. Why is that the case? That is the case because the Feynman diagram that I have used for muon decay is a contact diagram. There's just one vertex. See, I know nothing about the interaction. Once I go to higher energies, once we had higher energy capabilities of collision, then you were able to see what gauge bosons are actually transmitting this interaction. But these are early years. They didn't have knowledge that, I mean, there were always ideas, but they didn't specifically know that every time I have a new interaction, I must postulate new gauge bosons and so on. So they assumed a contact interaction. In this case, that's a reasonable assumption because this contact interaction means that whatever is mediating these kinds of interaction lives for a very short time. Okay? Now, That's a characteristic of any weak interaction. And that's because you can't really, to probe what is going on here, you need really high energies. Okay, it's not like the photon. The photon lives forever. It has, QED has, as I told you, an electron in this room and at the edge of the universe still have some attractive force between them. That's not the case for weak interactions. They knew from experiment that the range of the weak interaction is very short, because once you cross the nucleus, you don't see these types of things going on easily. Okay, so the range of the force is short. That was known. So then it becomes reasonable for you to simply shrink whatever is happening in between to a point and assume a contact interaction when you're trying to understand what is going on. Okay, a contact interaction may not always be a reasonable assumption for a long range force, but for a short range force you can start with that until you learn more. That's precisely what is being done here. Okay, so there is a contact interaction. That means there is one vertex, okay, as opposed to things like this, where there are two vertices, because there is a known gauge boson or known intermediate state. I don't know much about the intermediate state here, so I've assumed a contact interaction knowing that it's a weak short range force that I am dealing with. Is this clear? When you do that, you get this 4 fermion structure. Okay? Is that, can you see that? Because I have only one vertex. I'm trying to decide the Lorentz structure, but I have to put 4 fermions here. There are 4 spinors and one vertex. Okay, so then that forces this to have dimensions of 1 over mass square, so that the interaction term of the Lagrangian has dimension 4. Is that reasoning clear? Okay, so this, because you know, you have learned QED, you know that a vector is something that you could possibly choose. Okay, another possible choice open to them or open to us is Elint would be axial vector. So then again I would put G and I will put is this clear? Okay, so there is an axial vector choice, there is a vector choice. I can choose combinations also and construct Lorentz invariant matrix. So it turns out that, so this is what Fermi proposed. Fermi was the person who was trying to do this, among other people. So he first assumed this, and it turns out that, well, that is not correct. So why was that not correct? Again, you have to go to experiment to understand. What seems a theoretically reasonable choice has to be tested against experiment. Okay. So a significant clue regarding weak interactions came from an experiment on decay of polarized cobalt nuclei. Okay. So, in trying to understand what choice you must make, people were doing experiments. Okay. So, here's the experiment that showed that you see the cobalt nucleus has a total spin of J equals 5. Nucleus spin, okay? You cool this guy down so that these nucleons don't jiggle as much as they would normally do at higher temperatures. So you cool the thing down, cool the sample down, and you put a magnetic field. Okay, so that makes it easier to align all these guys and give you a definite spin in this direction, in the direction of the B field. So that was done. And then they waited for it to decay because they know that it will decay. Okay. So it decays, and to nickel, and nickel has J equals 4, and the decay is your typical decay that I pointed out as an example of weak decays last time. Okay? So you have a neutron that is decaying to a proton and an electron and an antineutrino. Okay. So this is the daughter state, and for instance, here's a possible configuration of the decay. Okay, so I need spin 1 in this direction because I have force sitting in the nucleus along the B field direction. So this is my applied B field. So these particles which come out must give me that additional spin 1. And this then is a good configuration for that. Okay. Another possible configuration, for instance, would be that I have the electron coming out like this, and the Noe bar going like this. This is also possible, which conserves electromagnetic, angular momentum. Is this clear? So these are, when rotated, are all naively equally probable, which conserve angular momentum. What is observed here though, in the experiment, when you observe the decay, you see that this doesn't happen. The electron does not come out in the direction of the magnetic field. Okay? But it comes out in a direction that is opposite. So, of course, I know that the neutrino, although antineutrino, I cannot see it, but must be recoiling opposite to the electron, which I can actually measure, whatever direction it's going in. Okay. So, and I know from angular momentum conservation that the Noe bar must have its spin like this. Okay. So this is a right-handed object. This is a left-handed object. And here I have a left-handed antineutrino and a right-handed electron. this is right-handed, this is left-handed, or negative helicity. Is that clear? Is this making sense? Okay, this doesn't happen. Experimentally observed. Okay. So what does that tell us? That tells you, once you of course confirm whenever you see something strange, you have to check it a million times to see that there's nothing else wrong in your setup and so on. And that's part of being an experimentalist, okay, before you announce some radical new result. So you see that the weak interaction happening here. This experiment is telling you that it couples to the left-handed part of particle spinner and the right-handed part of the antiparticle. Okay. So it has a preference. You do not couple to left-handed antiparticles or right-handed particles. That part of the Dirac spinner has to be removed or projected out, and you have to take the left-handed part, and that has to be built into the vertex. That you will project it out with a PL, PR depending on what is needed. Is that clear? So see, already the structure is different from here. If this interaction were like this doesn't project out special states at the interaction vertex. You would see both with equal probability. Okay? Is that clear? But you don't see that. You see this, but don't see this. And that is how you get an idea of what the vertex could be. So, so again, it stresses the important or crucial role that experiment plays when you're building new theories. Because theoretically, this is wonderful and simple. Okay? Or any of these choices are all good, equally good. But that's not what nature has chosen. So, learn that by looking at experiment. Oh. Alright, so having said this, this means so whatever interaction I build must contain this kind of. Therefore, is a final state particle. Okay, so the projection operator must be opposite of what I want it to be. I want it to be left-handed because that's what experiment is telling me. So I put a PR here. Okay, and then putting a PL here, I want a left-handed particle, a right-handed antiparticle in this state. So these are choices that will project out the correct state. Remember, I can put a projection operator here, okay, and so this is, I must put PL because there is final state right-handed. Okay, so when I pull this here, it becomes PL square, which is PL. Hence, these are equivalent choices. Right? I only need one operator. Is that clear? That projects out the correct combination. So this is a good choice, okay, for the interaction. This is like vector because this is multiplied by 1 minus axial vector because gamma rho gamma phi. There is a V minus A interaction. So it's a linear combination of two perfectly good choices. Is this clear? Any question so far? Okay. So also need complex conjugate choices to make the terms all Hermitian and real. So a complex conjugate of this, complex conjugate of this, so on and so. So nu E bar ER gamma rho E, and which is equal to nu E bar gamma rho PL. Okay, so you are building the Lagrangian, and you will need terms like this. So terms which project out a left-handed antiparticle or a right-handed particle will not appear in the Lagrangian. They must be left out. So there is a choice.
Sir, one question. What prevents us from writing a scalar-scalar interaction? I mean,
Nothing.
not without any gammas.
Nothing. That's a good question. So all of them are equal choices, but if you do that, you find that the answers you get don't match your decay rates or your scattering rates.
I mean, what are the experiments that prevent, tells us that we shouldn't write that? I mean, this selects that we have to add a B minus A type of interaction.
So here you have this clear experiment that is telling you that I have to select a certain helicity. I cannot do that in a scalar-scalar interaction. That is one thing. Okay. But it's more than that, because as I said, the answers you will get for scattering will differ, not by a huge amount perhaps, but will differ. See, because the constants are all the same, masses, energies, couplings. Well, not couplings, because the coupling is set by comparing it to the measured rate. But the answers you get, the distributions, the angular distributions you get will change, as we will see. In muon decay, we will put this V minus A interaction and calculate it, and then you see that energy distributions, angular distributions will depend on this choice. It changes the distributions. So distributions are something that you can measure, not for all particles. You cannot measure the angular distribution of a neutrino because you don't see it in the detector. But for an electron, yes. So you do have an electron here. So you can try to measure the energy distribution of the electron, the angular distribution. Those will depend on this vertex choice. Okay. So that's how you would discern. And then even before you start writing out this, you sort of knew that I have to select left and right handed. So you can't do that with a scalar scalar. Okay.
I mean some extra terms, not only this interaction but also a U-bar-type coupling, scalar coupling with both electron and.
So you're saying you could add.
Yes.
Huh. So when you do that, you should see a distribution that equitably treats left and right handed. Okay, so supposing I see 80% this, 20% this, then I sort of know that I have to adjust things. I have some combination which is, so one way I can do that is, see here I do, there's gamma rho and gamma rho gamma phi. I could tweak the coefficient here and put 0.3. Okay, and then I will see that this, they are not, this one treats it democratically because I know that from QED. So this would give me this combination also, whereas this one is actually putting these kinds of constraints on the distribution that you see. So I could, instead of adding scalar terms, I could also vary the coefficients here, because that would just mean putting a number. Yeah. Or I could add a scalar, do something. But then I have to see some evidence of this. If it's totally like this, then I know that the only term there has to be such that it gives me always this in there. Okay, so therefore now always I'm working with my example of muon decay. So L int mu decay must go as, let me put the equal to sign, minus 2 root 2 G F. I'll explain these in a minute. Rho mu bar gamma rho PL mu. E bar gamma rho PL nu E bar, I mean nu E plus charge conjugate, complex conjugate, sorry. Okay, so this is the electron nu E vertex. This is the muon to nu mu vertex. This is dictated by what I told you last time, that the family electron numbers are conserved. Okay, so I don't have nu mu bar and this electron neutrino sitting here and the muon and the electron in one leg. I don't have those because the vertex must conserve these family electron numbers. So that was decided then, but we didn't know that we had this gamma phi structure. Now we know that. So that is put here. Okay. Again, it's a 4 fermion interaction. The constant G is now was usually written as Gf because Fermi was the one who developed this theory. Has dimensions of mass to the minus 2, and this is a convention. Okay, so it's just a number which can be absorbed into G Fermi. but is not absorbed because G Fermi has written this. Is that clear? Okay. When you go to the gauge theory of weak interactions, the coupling constant will no longer be dimensional, because you will have QED or you will have this 2 to 2 scattering with an intermediate gauge boson in between. Okay, it's not a contact interaction anymore, because you are at energies where things can happen and you need a full theory. So we will of course study that, but this is a valuable lesson. First of all, this theory works very well until you go to high energies, I mean in giving you results. But it has issues because terms in the Lagrangian require a dimensional coupling. Okay, so you must have studied in your field theory that when you have dimensional coupling constants, you have problems with renormalizability. But we are not worrying about that here because we don't have a full theory. The Fermi theory actually is non-renormalizable because of this. But that's not an issue at present. We just want, we're working at low energies, we want the right answer. When you go to high energies, you have problems. But then when you replace it by a full gauge theory, which still collapses to this at low energies, then you sort of are fine. Okay. So that is renormalizable. Okay, so this would be my term for muon decay. Okay, so let me redraw the diagram. These are my labelings. Okay, K in the final state and P is in the initial state. So my matrix element is minus I 2 root 2 GF muon, neutrino and muon in one leg. See, here there is no intermediate particle, but when there will be in the full theory, then this contact point will separate into something with a gauge boson. So then this will become one vertex, this will become another vertex, and there will be an intermediate particle here. Okay. So this current must conserve muon number. So I am anticipating that and putting this, putting the muon and muon neutrino together in one current. Okay. In the contact part, I don't have to do that if I didn't know about lepton conservation and about the fact that this eventually will be one current, this will be one current, this will be the second.
Sir,
So it's being built with some advanced knowledge of how things are. Yes.
if there is a propagator or gauge boson kind of thing between this mu and the three outgoing particle, then there are two different type of interactions would be needed, and the vertex factor will be different. Because from mu to there is a propagator, and
So in a scattering situation, there would be more than one diagram. See, you need a propagator that is carrying charge, right? Because charge is disappearing. If I think of this as one current, then negative charge is being replaced by charge 0. Okay, so that must go here, and I can think of this as an incoming nu E. Okay, that receives that negative charge which is being emitted from this and transmutes it into an electron. Okay, so that is one. This is a charged current interaction, because the current is the intermediate particle in the gauge theory will be carrying a charge for this kind of current. Okay. So it's easier to see this in a scattering process. So here's a scattering process. Okay, so this must carry away, say, positive charge for this to happen. This intermediate gauge boson. Okay. So this charge will arrive at this vertex. Okay. So I will have a E minus, which will get neutralized, and I will have a nu E coming out. So charge is conserved, electric charge is conserved at each vertex in this manner. Okay, so there is a in a process like this, there is this diagram. Okay, there are processes which are also which have two diagrams. Okay, a charge current and a neutral current diagram. So something like would have one diagram where I have to exchange a neutral current weak gauge boson which is not charged. Okay, but I could equally well have nu E, E minus, W plus, and E minus, okay. Same final states, same initial states. So I would be adding these two. Depending on, but for this I have to know that I have such gauge bosons which exist and will mediate such interactions. So I have to have the full theory, which I don't at this point. So I am not talking about these things because at present we just want to do a simple Fermi theory type understanding of what this is. But here you can see that when eventually you will have a theory, and then to conserve lepton number, this must be mediated by a charge current particle. That I am pointing out at this stage. There are other interactions which can have diagrams which are both charged gauge boson and neutral gauge boson, giving with the same initial and final state. Is that clear? But we are not worrying about that now because I haven't come here yet in the course. Okay, so I'm writing this based on what we have seen already. Sorry. Skip this. Now I move to U and V spinors. V2 bar, PR, gamma sigma. U1. Is this clear as a corresponding? I'm just writing down the term here, UA, U3 bar for this. Correct? Okay. Sorry, yeah, I mixed up these matrix elements. So this is okay. And U1 bar gamma sigma PL V2. Okay, this should be correct. Alright, so this is my UA and this is my U3 for this outgoing muon object, muon neutrino, and U1 and UV2 here correspond to this. And it's a contact interaction, so all of these are written one. Okay. So now I can also write down M star. Just the complex conjugate of this. Okay, just flipping these things. Left becomes right and so on and so forth. And is this clear? So now I can write down mod M square. And this comes out to be 8 GF squared from the 2 root 2's. U3 bar sigma PL QA QE bar PR gamma rho U3 U1 bar gamma sigma PL V2 into V2 bar PR gamma making sense? Okay, just contracted this and gotten this. Is clear? Now what do I have to do as the next step? What's the next step in all these calculations that you do? Do the spin sums. Okay. I am again using the fact that in spite of be projecting out, in spite of the interaction projecting out specific spins, okay, doing the spin sums is okay because anyway I will not get contributions from those spins which are left out or not allowed by the interaction. So I am using these relations for spin sums simply to simplify my reduced matrix element square. So half sigma SA is UA bar is half PA slash plus M mu. I will not neglect the muon mass, I will neglect all other masses. Muon mass is 105 MeV, electron mass is half an MeV, neutrino masses are not known but are definitely less than 10 to the minus 6 MeV. So all those things are being used here. So sigma S1 U1 bar is K1 slash sigma S2 V2 bar is K2 slash and sigma S3 U3 bar is K3 slash, and this will be used and the usual trace trick will be done which you are familiar with by now, and you will get half sum over spins I'll get these traces, so be sure to check what I'm doing. Into trace. Okay, so I've skipped one or two lines here because you've done these things many times by now. See, now these traces will involve some identities with gamma phi's in them. Okay. So I've given you some trace theorems already in the homework, but maybe these involve some more. So I'll go look things up and maybe give them to you in the homework so that you have all the identities that you need. but I'm going to go ahead and use those identities. So I can do all these things, and this gives half some spins mod m square equal to 64 gf square pa dot k2 times p1 dot k3 after the traces are evaluated. Okay. So this is three body decay, and I have derived expressions for the decay width of three body decay. Okay. So we are going to be using that to evaluate this. So recall expressions for three body decay for case we used big M there, that is my mother particle, that's the muon mass, and M1, M2, M3 equal to 0 because the daughter particles are assumed massless. And this approximation is good whenever you have a heavy particle decaying to much lighter objects. Okay, so I have to evaluate these objects. Okay. So I can have the muon at rest. I can go to the frame where the muon is at rest, and then let me choose that the K2 is along the z-axis. Alright, so just to remind you, the K2 was the Nui bar. This was the label. Rotated things to a frame where the neutrino, electron antineutrino is being emitted along the z-axis. Of course, you can make a number of choices, but for what I want to do, this is convenient. So my PA is mu 0, 0, 0, and my K2 is E Nui bar 0, 0, E Nui bar. Is this clear? Okay. In this frame. Therefore, PA dot K2, which is one of the objects I need here, is equal to mu E nu E bar. The other object K1 dot K3 is but K1 plus K2 of course is related to K1 plus K3 is related to PA and K2. So this is a half PA minus K2 square plus 0 plus 0. Setting these two to 0 because they are massless effectively. Okay, is this fine? So this is PA square plus K2 square minus 2 PA dot K2. PA square is mu square. And the energy of the K is this. So putting those things. Okay, this is an expression I have. Is this clear?
K1 square and K3 square equals so I get 0.
These are the masses of, so since I'm assuming them to be negligible. Okay. So recall that your three body expression was So, for this case of muon decay, I can choose D electron E bar GF squared equal to pi cube, just putting in the matrix element, okay, and making choices for what I want to take as E1, what I want to take as E2. They correspond to this and this. The electron is something that's observable. Its energies I can measure. So I want to choose the quantity of interest, which earlier also I had pointed out. Whatever you are interested in, we are choosing that to be with subscript 1. So that's why the electron is being chosen here. M mu squared E mu E bar minus 2 M mu E mu E bar squared. Okay, just this object being put here. Now you have to make a habit of checking dimensions. Alright? So if this were mu E nu E bar and this is mu E nu E bar squared, then you know that you missed something. Okay. Similarly, you can check whether this has the right dimensions, putting in energies and dimensions of this, and do dimensional checks at various steps to see that you haven't done something wrong. That is something you should make an habit of. So you have to look up the limits that I had for three-body decay for the case where all daughter particles are massless. That simplifies the limits, and that is the case that is applicable here. So I'm interested in this distribution because that's something I can observe. So I will integrate this out. Okay. So if you go to the limits, we had a limit for E2. I will take this as E2 corresponding to this, and I will look at what the limits for the E2 integration are, which I have given you in the general expression for a three-body decay, if you look in your notes. So do So we had derived these limits, okay? M by 2 minus E1 less than E2 less than M by 2. I'm going to use that for the case when daughter particles are massless. So D big M in this case is mu, and it goes from M2 minus E1, so it's EE here, all the way up to mu by 2. That's the integral limit for dE nu E bar. Then I have GF square 2 pi cube mu square E nu E bar minus 2 mu E nu E bar square. Okay. So this is equal to dF square over pi cube mu square E square over 4 minus mu E cube over 3. And therefore this is the distribution I'm interested in. I pulled this to this side, and this is GF square mu square E square over 4 pi cube into 1 minus 4 E over 3 mu. Predicted energy distribution of the electron based on my assumptions of the vertex and so on. Okay, so now I can go and measure experimentally, but I can plot this, right, as a function of. So plot it. On the x-axis I take E over mu, this object. And I find, okay, so this has certain values. I plot this function, I find that it peaks at 0.5. the electron energy when it is half of the muon energy. There are three objects in this decay, so there's a limit to how much energy one particle will take away, and the maximum energy it can take away is half the muon energy. So this distribution looks like this when plotted. So, and at this point where the distribution is maximal, the electron is carrying half of the muon rest mass energy. Okay, so what does this look like? This means that to conserve momentum, these two neutrinos, there's a neutrino and an anti-neutrino, which are the remaining daughter particles. They must recoil almost together, totally opposite in the opposite direction. When the electron is in the direction opposite to the electron, both of them should be more or less collinear when the electron is taking the maximum energy. So my geometry of the decay looks like this. Electron must be left-handed, so its spin is like this. This decay at rest, remember. So there's one of these guys which is nu E bar. That must be right-handed, so its spin is like this. And there's another guy, nu mu, and that has spin like this. So you can see that this, of course, is an allowed configuration because the muon has spin half. Although when it is at rest, its helicity is not a well-defined object, because remember, helicity is spin times momentum. So whatever direction its spin might have been in, the decay then will happen in a way that half spin is left over. And it sort of tells you what the spin of the muon was, the spin direction. But this is the configuration that you will see for the maximal rate of decay. This is the distribution in energy for now, let's look at the other end. Smallest possible electron energy. I know why somebody's poking there. Yeah, is there, do you have something here? I don't know why they keep looking in all the time. Maybe something is scheduled. Can you just ask them what the problem is?
Here will be lecture from 3.
Yeah, okay. So, let me look here. Okay, when the electron energy is close to 0, that's what this means, right? This point. Okay. So when the electron energy is close to 0, let's assume it's at sort of at rest. Okay. So then the muon decays. But now, if this is the neutrino, this is the other neutrino, then this should be left-handed. This object should be right-handed. Okay. So the electron is simply just sort of sitting here. Alright. Now the neutrinos are being emitted back to back. So the electron neutrino, the effect of this object is that, supposing it has some small momentum in one direction, let's assume that it has this, so it's left-handed. See, so something like this, it has to have some momentum. So its spin, then because it is left-handed, it has to be either in either direction. So then you can see that you are in a spin 3/2 configuration here. Okay. Is this clear? See, if I look at, if supposing it's emitted here, alright, then for me to get half spin net, this has to be in this direction, okay, and in this direction I have, this is a left-handed, this is okay. So depending on what this is, you will see that you are getting a 3/2 configuration here, which reduces your probability that, I mean, you will start violating angular momentum conservation in this situation. So the distribution then is falling due to the fact that you have one disallowed configuration here, but it's also falling because the energy of the electron has gone to 0. Okay, so the decay rate falls due to that. Although you do have one allowed configuration, for instance, this is allowed if it were moving like this with small energy. But because of this proportionality, so here the drop is in the cross section is due to the expression of the decay nature of the distribution itself. Here it is maximal because of this configuration. So in either case you cannot violate angular momentum, but in this case you get a maximal configuration where you know that the electron and the two neutrinos are recoiling back to back. And you also know the direction of the initial muon spin. Is that clear? So I will do more about this. We'll look at how the distribution changes when you have, say, a neutrino energy here. You can't measure that, of course, but it's still instructive to see how that works. Okay. Is that okay? So we'll stop here since those people outside are getting anxious. But there is a lecture on Monday. Okay. At 1:30. And I'll send out an email about that and about the exam.